एक सेकंड थांबा.
Good evening, everyone, and welcome back to day 6 of our astronomy week. Today we are joined by Jitendra Joshi. He's an alumnus of Ferguson College and he graduated from the Department of Physics. He has done his bachelor's project on the study of variable stars through CCD image analysis and is currently pursuing a course in astronomy and astrophysics in the University of Bonn in Germany. Some of his fields of interest are star clusters and galaxy formation. He was also a member of Astro Club when he was in our college, and we're very fortunate to have a senior like you here today, and we all welcome you.
Thank you. And I hope everyone can see the cursor here. So today my topic is variable stars. Especially I'll be talking in the first half about how stars evolve, some basic physics that I find will be interesting in the later part when I explain about variable stars. So as usual, my first question always comes is uh, what are stars? And do we have a precise definition of a star? So it's more like defining a continent. So when we say a continent, normally geographically, we say it's a large expanse of land covered by sea or ocean on all sides. But in that case, Africa, Asia, and Europe will be a single continent. But again, we divide it politically, so we have these three different continents. So in geographical terms, we say that there's no precise definition of continent. But do we have a precise definition of a star? Well, it kind of we have, and no, we don't. So we say a star is an object that radiates energy from an internal source, mostly through nuclear fusion processes. And the second point is it is bound by its own gravity. Now, when we say radiates energy from an internal source, these excludes the planets that we have because they don't radiate energy from its internal source. So planets normally reflect light from the sun that we see, especially when you see Venus and Jupiter in the night sky. Those are mostly reflecting light from the sun. So these planets obviously are not stars, but this definition exclude this. But again, if you say that only this is the definition of a star, which radiates energy from an internal source, then obviously when we see a coal burning or when you heat iron rod, it also radiates energy. It glows red hot. So then by the definition of that, it also becomes a star. So we again say that it is bound by its own gravity. And this we can say is a pretty much nice explanation of what a star is. But again, if you see this, I want you to put in the comment section what do you think is this object, and according to this definition, do you think this is a star or not? So let's see. We'll catch up this later after 5-10 minutes. Then, in when we see stars in the night sky, normally we see like we study. The scientists need to study the evolution of the stars, and for that, the very first step was the Hertzsprung-Russell diagram, HR diagram, the famous HR diagram. So HR diagram is nothing but a graph of stars, like it's a graph of magnitude or the luminosity versus the temperature. So as you can see, like here's the luminosity as compared to the sun, and we have the temperature on the x-axis. So normally when you see a star, so when a star is formed, it's normally in this region. So it's normally in this area where it has low temperature and the luminosity is also low because it's just a cloud of gas. So normally what happens is there is some nebula or a cloud of gas which then collapse under its own gravity, And when it collapses, initially it won't have much temperature or energy to radiate or form nuclear fusion. So during this process, what happens is once it gets dense enough, the hydrogen starts to burn. So by burn, I mean two hydrogen atoms, when they collide, it forms a helium atom and it gives out immense amount of energy. So this is the nuclear fusion reaction, which mostly happens in like stars in the very initial process. So when it's in the initial phase, it's in this part of the uh, cloud, or in this part of the regime of the HR diagram. And when the nuclear fusion starts one by one, the more the cloud collapse, the more dense it gets, the more energy it radiates, and so it moves up this diagram and onto this main sequence phase. So what is this main sequence phase? So the main sequence is nothing but the the main sequence is nothing but the a star which fuses hydrogen to form helium in its core is in the main sequence phase. Now, once it starts fusing hydrogen, it is in this part of the regime, and depending upon the size of the initial size of the gas cloud that is there. So if it's a one solar mass star, like the mass of the star is equivalent to that of the sun, so it will be in this part of the regime somewhere. But if it has a higher mass, then it will be somewhere up here, with higher temperature, because it burns more hydrogen, so it will obviously have more temperature and more luminosity. So after that, it goes up in this regime like this. It it goes through this main sequence phase, through the hydrogen burning phase. But once the hydrogen is depleted, no more hydrogen can be fused, then it goes up this instability strip. Some of the stars which are high mass stars, let's say stars which have mass higher than the sun, normally goes in this instability strip. And most of the pulsating variable stars, we'll see what a pulsating variable star means, but most of the stars which are pulsating are in this part of the regime. As you can see, the RR Lyrae, the Delta Cepheid are in this part of the regime. So most of the variable stars that we observe and we are interested in sometimes are found in this area, in this region. So what happens in this region, we'll also discuss it in details in the next few slides. So, but for the low mass stars, just like our sun or some other star, what happens is once it stops burning hydrogen, it can no longer produce it, does not have enough energy, does not enough density to further start the helium burning. So it goes in this white dwarf region, it collapses under its own gravity. There might be a few explosions and all, and in that process it forms a white dwarf or a neutron star. But so basically it forms a white dwarf because a white dwarf is nothing but a very dense and compact object which has a very high density, and the density is very comparable to that of the neutron stars, but not as dense as the neutron stars. It has, if you consider the amount of mass that it has and the volume, so if you consider a white dwarf which is of the size of our earth, then it will have the mass will be around 1,000 to 10,000 times that of the earth. So it is that dense. And also, like, so for a low mass star, just like the sun, it goes in the HR diagram phase, like in this phase. But for high mass stars, it goes in this way, and then afterwards it forms a white dwarf, or it might explode into forming a black hole and all. But that's a different process, a different theory. So as I said, most of the variable stars are found in this instability strip, and we'll see why it's called an instability strip and why we see pulsating stars in this region only. So first, when we say we have a star, we see that the star doesn't evolve as over human time scales, at least. So if you look at the sun, and if you are looking at the sun for like past 5 to 10 centuries, it's still the same. It has not changed much. So that means there are some equilibrium processes happening inside. There is pressure that is being formed from the nuclear fusion that is there inside. Also, there is the gravitational force that is keeping the star bound. So these equilibrium processes help in maintaining the star's radius, mass, helps in luminosity, then producing more energy as it burns hydrogen or any other element. So for that process, normal stellar evolution or during normal study of stars, what we do is, we, instead of considering radius as a coordinate, we normally choose mass as its coordinate. So there are various reasons for this, but you can see that this is a direct conversion. If you say the density is equal to mass upon volume, and if you rearrange and take the derivative, you can easily get this equation that the dr upon dm is equal to 1 upon 4 pi r square rho, where rho is the density. So henceforth we'll use mass as a coordinate instead of the radius. So as I said, it's the stars are in a long-lived phases of evolution, meaning it doesn't change a lot as it grows, as the time goes by, especially in human time scales. We'll see what do I mean by human time scales, and what do I mean by stars are long-lived. So normally the age of the stars is like small mass stars or the high mass stars. They range from like 10 raised to 7 to 10 raised to 12 years. So that's a very huge span of time. And for that to be happening, the pressure that is being created by the nuclear fusion inside the core of the star should be equivalent to the gravity that is being produced. So this is the equation that tells us that the pressure that is being produced because of the nuclear fusion or other processes, we see which kind of pressures we have inside a star, and is equivalent, the pressure that is being created is equivalent to the gravity that is being produced because of the gas and the material of the star. And that's why we see that our sun doesn't all of a sudden erupt or all of a sudden vanishes, because these processes are in equilibrium. They cancel each other out pretty nicely. And so one of the uh, important equation that we get out of this equation is the virial theorem. So virial theorem is nothing but the this equation for an ideal gas. This is the equation which states that the internal energy of the star is equivalent to minus the half of the gravitational energy that is being produced. An important consequence of this is, if you equate the total energy, then we see that it has a negative heat capacity, meaning unlike any other objects we see in our day-to-day life, as the star lose energy, it, instead of getting cooler, it gets hotter. So this is what this virial theorem tells us, and it's very important in studying stars and stellar evolution, because it tells us how the temperature varies as a star collapses or as a star loses its energy. Also, if you see, the more the compact the star is, it is more strongly bound, meaning we need more gravitational energy. And so we need, like, the gravitational energy is more, so we need more pressure to equate to maintain the equilibrium of the star. So to maintain this equilibrium, more the gravitational energy, more is the pressure, and as more is the pressure, we can see that the temperature will also increase. For an ideal gas, we know pressure is directly proportional to temperature. So the pressure increases, then temperature of the star will also increase. So that means more the compact the star is, the more will be its temperature. So these are some of the time scales. Now, what do I mean by time scale? We saw in this picture the hydrostatic equilibrium. So that means the pressure and the gravity is in equilibrium. But what if we disturb this equilibrium? What will happen? And so if we disturb this equilibrium, our question is, in how much time will we see the effect of it? So the first one is the dynamical timescale or the hydrostatic equilibrium. If we disturb the hydrostatic equilibrium, if you put some perturbations in those hydrostatic equilibrium, what will be the output? So this, the timescale at which we'll see the output is given by this equation. Similarly, we know that the temperature of a star also remains constant over time or over some period of time. So what this tells us, what will happen if we perturb the, we give some more temperature to it, what will happen to it. And nuclear fusion are taking place now. This tells us, what if we all of a sudden stop the nuclear fusion that is happening inside a star. Let's say if in the sun, if we all of a sudden stop the nuclear reaction, how fast will we see the output of it? So this is given by these three time scales. So now for our sun, if we see, the dynamical time scale is just 1600 seconds, but the thermal time scale is of the order of 10 raised to 7 years, whereas the nuclear time scale is of the order of 10 raised to 10 years, which means if all of a sudden the nuclear fusion inside a star stops, then it will take 10 raised to 10 years for us to observe some significant change. So we can see that nuclear time scale is much greater than the thermal time scale, which is much greater than the dynamical time scale. Also, I should mention this thermal time scale is also called as Kelvin-Helmholtz time scale. So that's why we have this subscript of KH here. And as the nuclear time scale is much greater, the rates is determined by these nuclear reactions. The rate at which the stars evolve is given by these nuclear reactions. And um, also, as you can see, the dynamical time scale is very small, and sometimes we do see some changes when we perturb dynamical time scales, and we do see some variable stars which are happening because of these perturbations in the dynamical time scales. But I should mention, if you see, this dynamical time scale is very small, 1600 seconds, and we can see that stars live for like 10 raised to 10 to 10 raised to 12 years, maybe more. So this means that when a star is evolving, whether it's contracting or whether it's expanding, it happens by a process called as quasi-statically. That means that once it contracts, it maintains its hydrostatic equilibrium as well. So there are very small, tiny changes which helps keeping the hydrostatic equilibrium in place and also keep the star from contracting or evolving. And as I said earlier, there are different pressures that is being created inside a star. So these are given by the different equation of states in a stellar interior. So this, now what kind of pressures do we know? We know the pressure is created by an ideal gas. So this is the normal ideal gas equation we know, where mu is the mean molecular weight, and so mean molecular weight is nothing but the mass of one particle, average mass of one particle that is there inside the star or inside the region that we are concerned with. So this is the ideal gas pressure, which everyone, I guess, is pretty known about. You have been doing this since 11th 12th, I guess. Then we have the radiation pressure. So quantum mechanically, we deal photons or light as particles. So we also expect that this will also give us some pressure. So this is given by this equation. And also, this is a bit of quantum mechanics, and I hope for some second year students who are still learning quantum mechanics, or third year students who might know what a degeneracy pressure means. So in quantum mechanics, we have that an electron can be only in one state at one time in its atomic structure. But if it's in its lowest energy state, all the electrons are in its lowest energy state, then no more energy can be absorbed. So this creates a pressure that is given by this electron degeneracy pressure. And this nr here represents non-relativistic case. So which means the electrons that are in its degeneracy state are not has a speed which is not comparable to the speed of light, which is very small, let's say, in terms of the way speed of sound or in those terms. Then this is the pressure that we get. This is a constant which is around in cgs unit, 10 raised to 13 factor. And it includes like different constants, such as pi is there, h is there. I don't remember the exact equation here. And so as the electrons move down, it's from higher energy state to lower energy states. As I said, the pressure is created because when all the electrons are in its lowest energy state, no more energy can be absorbed, or no more electron can go into any other lower energy state. So that's why we have this. But what if we add more energy? So in that case, the speed of these electrons increases, and what we get is an extreme relativistic case. Or in this, the speed of the electrons and the other atoms is comparable to the speed of light. And so we have this different equation for that, which is given by this. And again, this is not equal, obviously. This is of order 10 raised to 15, so 100 times bigger than this in CGS units. Also see the power here is 5 by 3, and here it's 4 by 3. So now I have explained what all the pressures are. But when I say these are the equation of state, what do you mean by equation of states and why do we need them? So basically, equation of state helps us describe the microscopic quantities, using the quantities that we know for like the density, the temperature, and the composition. So by the composition, if it's completely hydrogen, then mu would be 1.007. If it's completely helium, it will be 4 point something. But if it's a mixture of both, then we have to take into account some other equations, and we calculate mu in those cases. So this mu tells us the composition that is there inside the star. Rho tells us the density, and T is the temperature, obviously. So using these, we can calculate microscopic quantities and especially the pressure. So now if you see, these all processes are happening inside a star. So if you equate these two, so if we say that the ideal gas pressure is equal to the radiation pressure, then we can see that we get a direct relation between rho and T. And it will be like, I guess, rho is directly proportional to T cube. So with all these constant, these all are constants, so we can just, for the proportionality, we can just take it as K. So T is directly proportional to K into T raised T cube. So if in that case, if you plot a graph of T versus rho in log scale, then we should get a straight line. Similarly, we can do this for radiation pressure and electron degeneracy pressure, radiation pressure, and like for non-relativistic, relativistic, for each of these cases. And what we'll find is we get a graph like this. So this is a log of temperature versus log of density graph. And you can see the radiation and ideal gas is this dotted line is tells us that the radiation pressure is equal to the ideal gas in this regime. Similarly, this dotted line up to this point tells us that the ideal gas and non-relativistic electron degeneracy pressure is equal in this on this dotted line. This tells us similarly ideal gas and extremely relativistic degeneracy pressure, and this tells us about these two quantities being equal. Now, what are these graphs? So as you can see this here, these are nothing but the different stars with different masses. So this one is 50 solar mass stars, which means the mass of the star is 50 times that of the sun. And this is one solar mass star. This is zero point 0.7, zero point 0.3 solar mass star. So as you can see, for higher, as we move higher, this is for zero point 0.3 solar mass star. This is zero point 0.7. And so as you can see, as we move from low mass stars is very near the boundary of ideal gas and electron degeneracy pressure. So which means that in low mass stars, these two regimes, ideal gas pressure and non-relativistic electron degeneracy pressure, are important processes that is happening inside the stellar interior. And as you move up, as you can see, for one solar mass star, it's completely um, in the ideal gas regime. And as you so I should also mention one thing by here. When we say the density, we also can say that this is equivalent to that of the radius. So actually higher the density, it we say that we are near the center or near the core. So if you see that this entire part of the one solar mass star, that is, if we say this is the equation of state for the sun, then the entire interior of the sun is governed by the ideal gas pressure and not by any other kind of pressure. But for a low mass star, it might be governed by non-relativistic electron degeneracy pressure for densities which are higher. And for extremely big stars, extremely massive stars, especially 50 or even 100 solar mass stars, these, as you can see in this part, it crosses the boundary. And for 100 solar mass star, again it's almost completely in the radiation, on this line between the radiation and ideal gas pressure. And so for massive stars, for stars whose mass is are about 30 solar mass stars, then the stellar interior is mostly governed by these processes, by the radiation pressure, predominantly by radiation pressure and some part by ideal gas pressure. So this is actually one of the output I got from MESA, a software which is known as the Modules for Experiments in Stellar Astrophysics. So this you can uh, go search for this, and you can actually create a model of how the star evolves. We'll definitely see some of the simulations that I did here in University of Bonn. So we here saw how which pressure is important in governing the stellar interior. In this case, we'll see the energy is being transported, obviously inside the stellar interior. There is this pressure is there. We have the temperature gradient. By temperature gradient, I mean some part of the star will be cooler, some part will be hotter. Uh, so particles or the electrons and most of the elements might move from one place to another, transporting energy with them. So what are the three important stellar interior processes is the radiation, conduction, and convection. This is just briefly to tell you what exactly do we mean by radiation, conduction, and convection. This is an analogy, not exactly what we see in stars. So I mean, we know everyone knows what radiation is and how it can transport energy. And then we have the conduction and convection. So conduction we can see in everyday life, like when we are cooking. Normally we heat the utensils, we heat the pot, and it gets hot. That's because of conduction. And convection, we see when you boil water, we see that it goes in a circular phase. If you boil water, the hot part, the bottom part of the pot, which is hot, makes the water inside it increase the temperature of the water, which rises. And because of this, when it reaches the top part, it again falls down, because at the top part there is a colder region. So it means there is a temperature gradient. So do we need temperature gradient for convection, or do we need temperature gradient for radiation? We need temperature gradient for these both of these processes. um, but for radiation, we don't need, like, the temperature difference shouldn't be, it's not much, it's small enough. But if the temperature gradient is high enough, so let's say you're boiling water and the atmospheric temperature is, let's say, 100 degrees Celsius. Temperature is outside is, let's say, 50 degrees Celsius, and you're boiling the water at 60 degrees Celsius. Then you won't see those convective currents going up and down as neatly as it would if you boil the water at 90 or 100 degrees Celsius. So what exactly differs in convection is you have these bubbles. If you see, these bubbles are formed inside water which rises up. So uh, these bubbles are also happen inside the star. So bubbles are formed, and these bubbles tend to rise up, and as they rise they tend to increase in size because of the pressure that is being created, and especially to equate the pressure that is there outside and inside to maintain this bubble. So when it rises, it increases in size, and it might again burst open, and so it might fall back again. So these processes happen. uh, Convection is one of the most unknown um, energy transport, or one of the most unknown processes that is happening inside inside a star. if you could, in near future, scientists are trying to understand what convection exactly is. So if you are able to explain what a convection is, then I'm pretty sure you'll be famous, especially in the science community. um, Convection also has other um, complexities, such as it also helps in mixing. So what do I mean by mixing? So obviously there are lots of elements inside a star, like hydrogen, helium, some higher metals like carbon, nitrogen. So because of this convection, because of these bubbles that are formed, and when they go up, because of those bubbles, there's this mixing of all the elements as well. So this adds much more complexity to it. But convection is also one of the most efficient energy transport mechanism inside a star. So we'll see if when we say that the star is completely convective, which means that the energy transport mechanism inside the star is extremely good. And so even though convection plays a very important role in stellar evolution, still it's one of the most least studied, least understood mechanism inside a star. So this is the Kippenhahn diagram. Now, as I explained, we have inside a star, um, we know that there are different processes happening inside a star, and one of the most important process is hydrogen burning. And as I said, we have energy transport mechanism, we have this convection, we have radiation, we have different kinds of pressure. So Rudolf Kippenhahn, he created this diagram to better understand how the stellar interior works. So in the x axis is the log for the time left until collapse. So this is where the star is formed, and this is where the star dies, maybe through a supernova, or it forms a white dwarf, etc. And in this y-axis is the mass. Now, as I explained in the earlier slide, mass is explained in terms of, like, mass we can use as a coordinate, just like radius. So this means five. This is a structure for a 25 solar mass star. So a star whose mass is 25 times that of Sun. So this is its surface, because it covers the entire mass regime. This is 15 solar mass star, so we can easily calculate the radius if you want, but normally we don't do that. We just keep it as it is. So we say that this is the 25 solar mass star. This is the surface. This is where 12.10 per 10 solar mass is being there inside the sphere. So what you can do is you can imagine a sphere, and or imagine a circle of radius 25, and now take concentric circles inside it. And instead of measuring it through radius, what we do is, we instead of measuring radius, we measure the mass that is present inside it. So this is how this y-axis tells us about the radius. And now you can see here this blue region. This is nothing but hydrogen burning, that is the core. So as I said, this is the core. So hydrogen is being burned inside the core. Then after hydrogen burning is over, we can see that hydrogen burns in still in the shell. So shell, I mean the envelope that is there outside the core. So hydrogen burning takes place in the core, but as this star especially has a very high mass, so this is so after hydrogen burning, it also starts helium burning. And so you can see, for like a huge period of time, it burns helium. So as explained earlier in the HR diagram, if you remember the HR diagram, then this 0 to 6 on the y-axis scale, x-axis scale, sorry, is where the star is in the main sequence phase of the HR diagram. Once this is over, so let's see, yeah. So once this is over, it goes into the instability strip, and that is when this helium burning phase is there. And after helium burning phase, we also have helium shell burning. And you can see here, there is no nuclear fusion that's being there inside the in the core of the star. The burning, that is the nuclear fusion, is happening in the envelope and not in the core. but helium shell burning is there. After that we can see oxygen core burning, we have carbon shell burning. So these processes are being carried out. You can also see that after hydrogen burning, there is a sudden drop here, and this is all empty. The reason is stars also lose mass by various processes, but stars, especially high mass stars, lose mass. So as you can see, when the hydrogen burning stops, it has already lost some part of its mass, and in the helium shell burning, it loses a lot of mass. So some reasons why they lose mass is because of the solar stellar wind that we know, maybe because of some eruptions happening and all. So you can see that high mass stars lose mass, and this is very important, as later we can see that the mass loss is around 10 solar mass is lost. So you can say around 40 to 50% of the star mass is lost because of stellar wind especially. And this is taken only as a one dimensional thing. So what do I mean by one dimensional thing is, in this Kippenhahn diagram, this mass coordinate doesn't include, we only take it in one direction. So what we do is, let me see yeah, so instead of sorry, mm, hold on a minute. Okay, so instead, imagine this is a three-dimensional um, model. It's a three-dimensional ball. Let's say it's a star. So instead of mm, taking whole three dimensions, what we do is we just consider one dimensional part. So from the center, let's say till this point, let me take some other color. So from this point, we just consider this portion, and we only model our star according to this. So I'll again, in couple of slides you'll see what do I mean by model of a star. So this is only one dimensional. So if you want to see two dimensional, then it gets pretty complicated, because especially because of the convection, because convection can happen in all the three dimensions, like in three-dimensional space obviously. But as I said, convection is a very complex process. So for that, what we do is we just consider one dimensional thing, and we model our star and see if it's in agreement with what we observe. So this is just one dimensional model of the star, and you can see this, the metallicity Z is also very, very important. So here the metallicity is solar metallicities. But if the metallicity is low, then burning is faster. The reason being, metals help in cooling the star. So more the metallicity, the cooler will be the star. So less will be the nuclear fusion that is being taking place. So the star will appear less luminous. But in our case, what we are doing is we are just considering the solar luminosity. And yeah, so this is the Kippenhahn diagram, a very important, one of the most important diagram for understanding stellar structure. As you can see in this one diagram, you can see what all is happening. We have hydrogen, helium burning, helium shell burning. So this tells us the convective envelope. So convection does not always happen throughout the star. Sometimes convection happens inside the core, sometimes convection happens in the envelope. If convection is happening in the envelope, then we say, then there's a theorem, there is a proof. You can see a lookup on Google if you want, that we have, if there is a convective envelope, we'll have a radiative core, and if we have a radiative envelope, we'll have a convective core. So in this case, we have a convective envelope, and so we can say that the core is radiative. Mm, yeah, I guess nothing else. Yeah. So now we'll see some MESA simulations. So these are the simulations that I did for one of my course here in known as the Stars and Stellar Evolution. And MESA is one of the latest softwares, one of the latest simulations you can do to model the stars. Um, yeah, so let me first explain. This is quite complicated, but we'll not look up at each of these graphs. We'll only concentrate on this graph over here. This is nothing but luminosity versus temperature. So this is the HR diagram, like we can say, and we can see how the star evolves in its HR diagram phase. This is the Kippenhahn diagram, but on the x-axis we have model number. For the time being, let's say this tells us about the time, but I should warn you, this is not in linear scale. As we progress, we'll see this is does not happen in a linear scale. And here you can see some very important features like the mass of the star. So this is for a very low mass star, zero point 0.3 solar masses. This is tells us the age, the radius in solar radii, and effective temperature. But we'll just look at um, some of these processes. So yeah, so you can see how the star evolves. Now this blue is convective envelope, we can say. And so as you can see, in the early part it's completely convective, and in the later part it's not as convective. So let's just run this through. I'll let you know. You can see the age of the stars here in years, and you can see that low mass star, it in this regime has not lost much mass. It's very low. And also the radius, you can see here it's very small at the very ending part. So right now what's happening is there are the CNO chain, there is the PP cycle. So basically hydrogen burning is happening in the shell of these stars. What this red that's what this red thing is showing you here. And so let's just run through and I'll explain later in. Yeah, okay. So this is the initial stage where the star is still collapsing. That is the hydrogen burning has not started yet. And so yeah, now there is hydrogen burning inside the core of the star. So now look at part of the HR diagram, you'll see how it grows. So you can see it increases in this region. So this is where the main sequence evolution of it is. You can see here that here the in this part, the red part here, where it ends, so that's where the hydrogen burning began. And this now is where the hydrogen shell burning is happening. So that means if you consider this as the radius, then there is no nuclear fusion that is happening inside the core of the stars. It's only happening uh, in this part of in the envelope of the star. And you can see it has a convective envelope. And yeah, so this is there. And if you see closely, look at the radius. So see how the radius increases and decreases all of a sudden. So yeah, let's start from. So here we have the radius is 0.5 times that of the radius of the sun. And as you progress in the HR phase, it's again decreases because the gravitational collapse is happening, the pressure is there, so it collapses. But once that is over, the star begins to expand, and that's when you get these nuclear reactions happening in the envelope and not in the core. So note here that the star has not lost much mass, just 0.04 solar mass instead of the earlier zero point 0.3. And the radius is also again increasing here. and it again decreases. So this increase is uh, mainly due to this processes that are happening, the pressure and all. So that's the important part I would like to point out in this part. And this here actually tells you about the composition of the star. So this is again the radius. You can consider the interior. This is the core. This is the surface. And in this part, you can see that it's completely made up of helium. This is nitrogen, carbon, oxygen, and in the very early part. So let's say we go back to hydrogen burning. So here hydrogen burning has not started yet. So here these are the values that we have assigned to the simulation. So what we do is we can put out some parameters, like we can say that we want to model a star whose mass is zero point 0.3, and it has hydrogen, mostly made up of hydrogen and helium. Carbon, oxygen, nitrogen is also present. So this is tells us about the metallicity. And as you can see, this is in log scale. So this is mostly hydrogen and helium. Now if you go on, hydrogen burning has started, and you can see that hydrogen fraction decreases in the core and helium fraction has increased. There are other processes also happening, so that's why the carbon and nitrogen oxygen abundance is also changing. So now this is going on, and at one point we can see that it gets converted into um, yeah. So now you can say that this is actually a white dwarf in actually this regime actually. But yeah, this you can say it's kind of in the white dwarf phase. So you can see it's mostly made up of helium. So the white dwarf that is being formed is a helium white dwarf. So that means it's mostly almost 99% made up of helium. Now this is for zero point 0.3. You'll understand this better when we see zero point 0.1 solar mass star. So this is, let's say, this is how our sun must have evolved. And again, we'll look at all the other parameters here. Mm, so yeah, so this part is where in this regime is where the uh, hydrogen burning started. So this is when it entered the main sequence phase of the HR diagram. And now you can see here that there will be a changes. Also you can see right now it had convective envelope, but now the convective core here, but now it's here. You can see we are right here, so it has convective envelope. And this red part here in the let's go a few slides back. So yeah, so you can see a lot of processes happening, a lot of nuclear fusion is happening inside this star. So you can see hydrogen abundance in the core has depleted. We have this up here, the abundance is as it is. So there is a lot of changes happening inside the core because there's this nuclear reactions happening. And so this is how our sun will evolve in the future phases. And you can see now it's a red giant because its radius is 170, 180 times the that of sun. So here now there's these processes. The blue and red part is where carbon and nitrogen and oxygen burning is taking place. Now it is a white dwarf, and interestingly you can see the white dwarf is made up of carbon and oxygen, mostly made up of carbon and oxygen. So this is for a 1 solar mass star. And so this is a high mass star, 30 solar mass star. If you go beyond 30, then um, you'll get actually a better understanding. But this is a 30 solar mass star, and now this is where the it has entered the main hydrogen burning phase. And now you can see that it has a convective core. In earlier simulations we had convective envelope, but we have convective core. And so I mean, and if you see, it has lost considerable amount of mass, and as we progress we'll see that this is decreasing quite fast. So this was initially a 30 solar mass star, and now it's 20 solar mass star. Also, there are a lot of chemicals present now. There's a lot of activity going on. Core burning is there and all. So this is basically how we do simulations in one-dimensional stage, and we see if we can observe this. Now, after this, I'll start with variable stars, and I'll explain. As now you know how stars and the processes of stars is happening, you'll better understand how different kinds of variable stars we observe, or how variable star study will help us understand this stellar evolution process. But before that, I'd like to take few questions if you have till now, so that if there are any questions, then I can. Is there any questions till now? And yes, I asked one question earlier. What is? Sorry, hold on. Okay. Okay, so Bhavesh is asking, how can one pursue stellar astrophysics as a research career? What are the concept and tools required for it? Can you tell which type of experiments were done for plot in sixth slide? Okay, hold on. So I asked what is this? So has anyone answered what is this part? So this is actually a brown dwarf. So it doesn't fit into these two categories, but we still say it's a star. Okay, so slide 6. Let me go to slide 6. Okay, so can you tell which type of experiments were done for the plot in sixth slide? Okay, so these is not actually experiments, but this is, as I showed you the MESA data, the MESA simulation. So we model the stars by the processes we know, by all the processes that I told you: the radiation, ideal gas, non-relativistic pressure, then the equation of states. So using these processes, we model the stars, we simulate them, and see if we can get the desired result. So this is actually one of the output of the MESA simulations that I showed you. Um, I'll come to the first question later. And what will happen if a star doesn't lose mass during shell burning? Will it create the instability and will affect hydrostatic equilibrium? So if no, in that case, again, the pressure inside the nuclear reactions will actually increase, because more dense, the core will get more dense because more mass will be added to it. But normally this is just to show you that mass is being lost. We see these processes happening, even sun is losing its mass. So yeah, I mean, I guess that answers your question. What does the first graph means in slides 9 and 10? Okay. Uh, so I guess you mean in this and this. Mm, so this is the HR diagram, uh, and this is the Kippenhahn diagram I showed you. So that's why I shared only look at these two, not the other four. So this is the HR diagram, how a star evolves in its HR phase, and this is the Kippenhahn diagram. What makes a radiative core to change in a convective core? So normally a radiative core does not suddenly change into a convective core. You don't see that, but I can explain how radiation can convert it into convection. So as I said, radiation has needs some temperature gradient, some temperature difference. But if this temperature difference becomes too large, if this temperature gradient becomes too large, then this transport of energy, the way that energy is being transported, can actually fall back. Like the energy that is being transported from this level to this level, let's say, then if this difference is too large, then it will fall back because of various reasons. But normally radiative core doesn't exactly change into a convective core. If it has a radiative core, then it will have a convective envelope, but if it has a convective core, then it will have a radiative envelope. So I guess there is no other question, and I can shift to the main, not the main part, but I'll quickly tell you what variable stars are. Now, you guys will be saying, like, I should have explained more about variable stars because the topic is variable stars. But if you have understood all the processes that I have told you right now, then I hope you'll understand how stars vary in brightness in a much better sense. So, as I said, variable stars are stars whose brightness changes. So, this is the brightness that we observe from Earth for one star, and this is another star. So, as you can see, this star doesn't change in brightness, but this star has changes in brightness. So, this is a variable star, and this is not. And then there are various types of variable stars. I won't dwell much into each of these, but let's say the intrinsic variables are stars which change in brightness because of some processes happening inside the star, like pulsating, or if they erupt all of a sudden, then these are intrinsic variables. And extrinsic are stars whose brightness change because there are some external parameters, like if there is an eclipsing binary. And yeah, mostly we observe extrinsic variable stars which are eclipsing binaries. So I'll go into details about pulsating and eruptive. I'll quickly tell you what using the different processes, different things that I told you earlier, and we'll then go to eclipsing binaries. So as I said, it's there in this instability strip of the part. Like the pulsating variables are mostly there in this part. So Mira type is, it was the first variable star detected, and you can see the brightness changes from 2.5 to 9. So I should tell you that more is this number, more is the magnitude, the brighter the star is. Sorry, the more is the number, the fainter is the star is. So 2.5 is bright and 9 is faint. So also the scale is logarithmic, so it's not like 2 2.5 and 9. So this means that star changes brightness twice the magnitude. No, it actually changes by a bigger factor. And so as I explained earlier, there are a lot of processes. It's a pulsating variable. And um, because of all this energy transport that is happening, because of mixing, and because of these nuclear reactions, so you in this Mira type variable, it forms an metal oxides layer around it. So this is an opaque layer, so that's why the brightness decreases. And once it erupts, or once the core again starts energy producing, or once this so this opaque layers decreases the temperature, and as the temperature of the star decreases, the nuclear reaction will also decrease. And because of this decrease, this metal oxide layer that is formed will again uh, go back to its, like, it won't form this layer again, it will vanish. But again, when this process starts, it will have this metal oxide layer forming on the surface of the star. So this is what we observe, and this forms, like that's why we see this pulsating variable. Most of the pulsating variable are formed because some or the other element forms a layer around it. So this was the first part. This is another example, and the difference is, in first part it shows metal oxide layer. In this it forms some other metal oxide layer, like not this forms a TiO layer. In this I don't remember, but it forms some other layer. So we see two different types of dips. So you see this is again two different types of dips. So this is, it's actually what we call a light curve. Light curve is nothing but graph of brightness versus the time. But you can see how this star varies. Both of these are pulsating variable. RR Lyrae, this is one of the most important star in cosmology. It can be used fairly good enough to calculate distances. And so this actually, um, as I said, it's written here, after all the hydrogen is fused, helium starts to fuse in the core. So this helium fusion is where it enters the instability strip. So RR Lyrae stars are basically stars whose mass is much bigger, at least 10 times bigger than that of the sun, and it has started fusing helium in its core. So it has just left the main sequence, and these are what we see are the RR Lyrae stars. Then we have the Cepheid variables. Everyone must have, at least interested in this field, must have read about the Cepheid variables. So in this period, the period with which the brightness decreases is proportional to the distance to the star, sorry, is proportional to the brightness of the star. So you can see that if it's a if the period of this variability is 5, then absolute magnitude it's 1. So it has 1 magnitude. But if it has a 10, then it will have a 2. So it has a linear relation. So just by looking at the brightness, just by looking at the period, we can estimate the brightness of the Cepheid variable star. And from the brightness that we get through period, we can see if we get to see that the light is, like, is it dim, and if it's dim, how much dim is it. So it's like this can be used as standard candles. And so most of the bachelor students, I hope, know what a standard candle is. But to in short, I'll say that if you hold a torch, so if, let's say, I turn on this torch, so you can see the brightness of this. Now if I move this behind here, the brightness decreases because the distance has increased. So this is what a standard candle is, because the brightness remains the same. So these Cepheid variables can be used as a standard candle and can be hence used as a distance estimator. Now, eruptive variables, at the end of its lifetime, stars erupt, stars explode, and they form this nice, beautiful supernova, nova. So I won't tell you much about supernova, nova, but these are some of the examples. This is a supernova. A nova is these burst of happens when there is a white dwarf and there's a companion star. This companion star puts mass inside this, and this makes the stars explode um, once in a while. So depending upon this star, depending upon the companion of the white dwarf, we have different types. So in this, if it's a red dwarf, then it's a nova. We say if it's a sun-like star, it's a dwarf nova. If it's red giant, we say it's a white dwarf. Now I'll tell you about my bachelor's project. So my bachelor's project was on eclipsing binaries. So just like in solar eclipse, as you see, there is in a solar eclipse, moon comes in between Earth and sun, so the brightness of the sun decreases. So this is what we observe, but instead of moon and sun, imagine two different stars. So we have this star and we have another smaller star. So when these are side by side, we see that it has maximum brightness. But when the smaller star is in front of the bigger star, obviously the brightness will decrease. And this is the primary eclipse, because this is when, in this situation, is when the brightness of the stars is minimum. Then again, when the eclipse is over, it will have the maximum brightness, and when the smaller star goes back, it will have another smaller eclipse. And this process is being repeated, so it's a periodic process. And so you can see it's a primary eclipse, secondary, then again primary. So using this period relation, using this luminosity, if we can calculate the mass of the stars, we can actually calculate a lot of things, using eclipsing binaries. Exoplanets were first detected by using this eclipsing method. And not only that, just by looking at the eclipse and just by measuring different parameters like this period and all, they were able to calculate the density of the planet, which, I mean, for me, it was a great achievement. And one of the interesting thing I find, that's because just by looking at the brightness, just by looking at the composition, and just by looking at this light curve, you can easily calculate what the density is. Now, my target star, or the star that I studied, was Algol. So Algol was the first variable star discovered, which was not a nova or a supernova. And it is also called a demon star, because in earlier days they used to see that there is a star in the sky, but all of a sudden, after 2 to 3 days, it vanished. So they said that it was some demonic activity, and so they said it was a demon star. And in this is the Perseus constellation. And here in the head of Medusa is where they said that we have the Algol star. So a nice analogy to saying Medusa and a demon star here. So so Algol is basically a three triple star system, but we only see the eclipse of Algol A and Algol B. And this image was taken from this interferometry in, I guess, California. So again, the same interferometry made this small animation to help you understand how brightness changes. So if you see, when this part goes behind, it has uh, this this is when it has a maximum brightness. The star will have maximum brightness, and when it comes out, it will again, this will have a minimum brightness. And this, if you combine this total brightness, then it will be the highest. um, so how did I approach my bachelor's project? So I hope there are second year, third year students of bachelor's. So here is some of the procedure that I would like to say. First one obviously is the literature survey. I read books, a couple of books, not whole books obviously, but some part which was necessary. Then you visit different sites, such as for variable stars, there is the American Association for Variable Star Observers, which AVSO. Then there are various other sites which can give you better information about variable stars. Then I did the equipment survey. By equipment survey, I mean I looked up at what equipments did I have, and is it possible for me to take readings up to which magnitude, which star is feasible for me. And also I did my experiment just by in using one DSLR camera and a tripod. That were my only equipment, and obviously laptop and softwares were there. Then finding the right target star. So as I said, this Algol changed its brightness in 2 to 3 days. So it was okay for me if I observed it for like a week continuously and see if I get any changes. Then collecting the data, I mean, by after I got the target star, I went up every night and took photos of the star that I wanted. Then I used software known as MaximDL. There are various other software. Like there is IRAF, there is Spiraf, there is Tele. You can use for image calibrations and all, and finding out, doing the astrophotometry, I mean calculating the brightness of this star. That's in the data analysis process, and at the very end, when you get the data analysis right, start writing the report. and keep calm and hope for the best in all these processes. Hope that everything goes well. If not, go back to earlier step, do everything again, and see where you went wrong. So this is the output, and so I'll like this is what I did. This is a bit of, I'll say, amateur stuff, because going every night taking readings and all. You can also take readings from AVSO. So these points, these 3 points, I've taken reading from an observer with this ID. So if you are interested only in data analysis, then you can obviously go on this AVSO website and see how these things are there. Like these light curves, you can plot the light curves and infer things out of it. So I'll tell you what the ongoing research is. So as I said, in the binary system, in the earlier, the novas, the mass is being transferred from one star to another. So what is the effect of that? Again, modeling evolution of stars is one of the most important ongoing research. It's more of a theoretical process than, like, this is more of a theoretical thing. But if you if you can model the star which is resembles exactly what we see, then that's the aim of this. That's main goal and a good achievement as well. But we are restricted, as I said. Convection is not helping us. Three dimensionality programming is not very good. There are n-body simulations, but there are a lot of processes as well. So taking into account all these processes, there's a lot of research going on. Also, using stars and using the spectra of stars, you can study the ISM, and there are many more topics which you can explore, or you can see that the research is being going on. So stars are basically like, in yesterday's or day before yesterday's lecture, you learned about cosmology, and most of the cosmology parameters that you saw yesterday or day before yesterday, like the Hubble constant and all. Hubble constant initially was calculated using Cepheid variables, stars. But sometimes some parameters like the equation of states that you saw in day before yesterday, the omega parameters, they are calculated using galaxy clusters. Some parameters are calculated using star clusters, but these are basically in in principle made up of stars. So study of stars is very important in knowing how the universe has evolved over time. And um, so yeah, study of stars. Everyone looks up at in night sky for stars, but when it comes to studying, everyone wants to go for GR theoretical stuff. But if you explore this option of observational thing of observation of stars, it's also a very important and very interesting field. So I hope some of you will be interested and can come up with solutions for especially convection in stars, the mass transfer and all. And for that, here are some of the books I'll recommend. This book is highly recommended if you want to know more about the processes, all the things that I said right now. Do give a visit to this American Association for Variable Star Observers. They have a lot of information, they have a lot of projects available as well. um, do give this a visit. These are some of the other book, but I'll highly recommend to search for this book by Robert Kippenhahn and Weigel. So thank you. And is there any more questions? I hope the talk was not too long. Mm, do variable stars maintain their periodicity? Yes, some stars obviously does, like Cepheid variables does. At least in human timescales, they do. So as I showed earlier in previous slides, as you can see, the star doesn't remain in the instability period for long, but it remains in that period for at least 10 raised to 4 to 10 raised to 5 years in that instability period. So it will obviously be pulsating during those period. So on human time scales, no, variable stars does not do maintain their periodicity. Sorry, but for stars, for stellar timescales, no, they don't maintain their periodicity, obviously. Any other questions? And yes, if you want, you can definitely contact me in this address. If you want any help, if you want to better understand these concepts, if you're interested in running the Mesa software, it's a bit complicated, but if you're interested, do give a visit. Thank you.
All right. Thank you, Dada, for that wonderful lecture. It is truly a pleasure to have you here. And we all really thank you for taking out the time to come and deliver this lecture. And to everyone watching, we still have more in store for you. So in this astronomy week. So stay tuned, stay safe, and we will be back with more.